Hello. This lecture will cover pages 50 through 59 of my lecture notes. So please print those pages out and have them in front of you as I present this lecture on describing logic circuits Part D, working with OR and AND gates. We're going to start out on page 50 of the lecture notes, and make sure that you have page 40 of your lecture notes. This Boolean algebra theorems and laws handy, because we're going to be using this, so have it out and ready to refer to. Boolean theorems that pertain to both the OR and AND operations. Theorem 13a is the distributive law, and it says that if you have x and the quantity y or z, it's the same thing as x and y or x and z. In other words, if you take a look at this part of the expression here, it is a x input to an AND gate and then a yz input, or that's the other input to the AND gate. And the output expression is your x and the quantity y or z. Through the distributive law, this circuit is identical to this circuit. This says that we have two input AND gates that feed into an output OR gate. So this OR function is the output gate, and this is x and y, or x and z. These two circuits are identical. But keep in mind, if you were going to build this circuit or this circuit, this would be the more beneficial. Why? Because it uses less gates. Remember back when we started talking about this chapter, we said this. We said we're going to use Boolean algebra, and why are we going to use Boolean algebra? It requires fewer chips, therefore it's going to cost less expensive to build, it'll use less power, and it's easier to troubleshoot. Keep in mind that Boolean algebra is very important to reduce the logic and get those benefits out of it. Notice the truth table here for the output A, which is this output, and the truth table here, you put in your ones and zeros and you go through the different states here, you get identical outputs. When the truth tables are identical, the circuits are identical. Also, if you look down here, we have A or B and C is the same thing as A or B and A or C. Now, this right here is a break from regular algebra. This is Boolean algebra. This isn't true in regular algebra. But if you take a look here, the proof is, here is A or B and A or C. And if you take a look at page number 40, Theorem 13b allows us to distribute this. That's more or less just like an algebra class. Theorem 3 gives you this, 13a gives you this, Theorem 6, 3, 6, 2 gives you down, and the proof is that this circuit being implemented, here it is the same thing as this circuit. Now, I didn't draw the circuit, but if you draw the circuits, let's see how many gates this circuit would take. Well, it would take an OR gate, and it would take a 2-input AND gate. That's 2 gates. Over here, you'd need a 2-input OR gate, a 2-input OR gate, and the output would be an AND gate. That would take 3 gates. So this would be a better solution. Take a look at page number 51. We have the absorption law. It's Theorem 14. X or x and y is the same thing as x. And here's the proof. 13a gives you here, Theorem 13a gives you this from here, 6 gives you this, and 2 gives you this. So what's this really telling us? Well, don't forget, these literals are nothing more than signatures. It's just it would take too much to write, if these are signatures, to write it all out. But for instance, let's pretend that x is an error signature, and y is going to be a data ready signature. So here's the implementation of that circuit. If you take a look up here, it's x, which is error, or That's the output gate, or the AND of X and Y, which is air and ready. And it produces the output, air or air and data ready. But this whole thing can be replaced with simply air, with simply X. That was the proof up above. So this is going to take two gates, and it'll solve the solution for you on your design, but you really just need a wire. So you save a lot of money and a lot of troubleshooting and a lot of possibility for breaking, for errors, for bad IC chips. So look this over. Make sure you understand it. And down here also, A and A or B is the same thing as A. And if you follow 13A, you get here. Theorem 3 gives you this, and 14 gives you just A. So again, this is a reduction technique that you'll use. On page 52, the Boolean algebra, equivalences. If you have 0 barred, you get a 1. You know that. 1 barred, you get a 0. And 3, look it over. 4 and 5. X barred is just X. And don't forget, these X's and Y's and Z's are just signatures. We're just abbreviating them with the literals. Makes it easier to read. Boolean theorems, if you take a look, this is theorem 1, 2, 3, 4, and here they are on page 40. 1, 2, 3, 4 has to do with AND gates, and 5, 6, 7, 8 has to do with the OR gate here. So that's all we're looking at. 1, 2, 3, 4, and this shows you the circuit equivalent. 5, 6, 7, 8. So you have to look at page 40 the same time you're looking at this to understand what's going on. You should have these memorized. They're pretty easy to understand, all these. Page 53. Any logic circuit can be completely described using Boolean operations of AND, OR, and NOT. That's a pretty powerful statement. For example, I want you to write these midterms and write the output, given A, B, and C. So stop the video and get on page 53 and see if you can work this out, and if you get the same thing I got. Another example down here. Another example. Go ahead and stop the video, work this out, see if you get the same thing I got. That's important. Be careful here. I want to show you something that's not in your notes. A barred or B barred is not the same thing as A or B, the whole thing barred. Now, if you take a look up here on this first expression, here's the circuit for that. An input gets barred, and then another input B gets barred, and then the whole output, the output is the OR gate. Up here, you have A or B, and then the output's barred. This is not the same thing as this. They're not equivalent, and the circuits show that. Make sure you understand that. Down here, same thing. A barred and B barred is not the same thing as A, B, the whole thing barred. The A being individually barred and the B being individually barred, that's inputs. That's input sections. When the whole thing gets barred, that's output. That affects the output. These circuits are not the same circuit. Page 54, you might want to stop the video. And I want you to work this out, and work this one out, and make sure you get the same thing I did. Here's the answers. Page 55, same thing. Work this out. Logic circuit diagram can be implemented directly from the Boolean expression by just working backwards. Example, I want you to construct a circuit with this Boolean output. Stop the video, see if you can get it. Here's the answer. Here's another example down here. You have to know how to do these. Once you catch on, they're pretty easy. Page 56. Little bit of generic rules. You can read them over very carefully. And then here's an example. Here's the answer. You can stop the video. Excuse me. You can stop the video and see if you can get the same thing I got down here through Law 1. Page 57, another example. Try it. Here's the answer. Page 58. The truth table for a circuit can also be found. First, obtain the Boolean expression for the circuit. Well, here we have a circuit. You can stop the video and try to get the same thing I got. Here's the output. X is equal to A and B, right here. That's an input gate. Or, there's your output gate. The OR gate ties these two together. There's the output. And B bar, or C. B bar and C, sorry. These are called midterms, min terms. These, you can refer to these as the inputs. These are the min terms. Here they are. Next, fill in the appropriate truth table entries based on the Boolean expression. So what I do, I mean, you could go, here's all your possibilities, 0, 0, 0 through 1, 1, 1. You list them in order, sequentially, so you don't miss any state. There's 8 states there. And then all you have to do is, no more will you put zeros and ones and go through it and ones and zeros and get a 1 or a 0. You don't have to do that. You look at the output, you look at the Boolean expression here, and this says you get an output when A is high and B is high. That's A, B. Well, A and B are both high here, you get an output. Oops, let me move this up. A and B are both high here, you get an output. A and B are both here, you get an output. So these midterms are ones because of the A and the B. Now, where is B low and C high? Here. B is low and C is high. That's a midterm. And B is low and C is high. And there's another midterm. I wrote them out here. So you see where I got the output. Guaranteed, if you go through ones and zeros the long way, this is the X will be a 0, 1, 0, 0, 0, 1, 1, 1 for this sequence in this order of inputs. A lot easier to work. Matter of fact, on page number 59, I want you to try it on your own. First of all, I want you to get the Boolean expression up above, and then use the same technique I showed you down below by just looking at the Boolean expression and forming the truth table. When we go through our design in the next chapter, this is going to be very, very useful to understand this. So make sure you try this on your own, because if you're going to hit a wall, I want you to hit it on your own so you can learn from that. I can't stress that more. You're really going to like when we start getting into the design here of the combinational logic circuits, which is coming up. It's very impressive and you're going to enjoy it. But you have to understand these basics, so study them. This concludes the lecture.